for this lecture video, we'll continue with our variational approach to the helium atom. This is our sort of second attempt. Our first attempt, we sort of used the variational approach, but we did not use parts of it. We didn't actually go as far as introducing a variational parameter. We proposed some solutions to a simpler separable Hamiltonian, and we used those as approximate wave functions, and then we calculated a sort of variational or approximate energy for that system, and we got a result that was about 5%, had about a 5% difference from the experimental or higher level calculation result. And we don't just introduce a parameter willy-nilly. We're actually going to use some reasoning to try to sort of intuit a useful parameterized approach. And our concept is based on, or rather our parameter is based on the concept of screening, which you may recall from other chemistry courses as one of the ideas that helps to explain periodicity. So we know that, say, lithium, sodium, and potassium, they're in the same column of the periodic table, and they have some similar properties, including, say, a similar ionization energy, because they all have one valence electron. That's part of it. They all have one sort of electron in their outer shell, or one sort of valence electron. And but the other part is that the other electrons are there, but they're closer to the nucleus. And the core electrons, we're going to call them core electrons, say in the case of lithium, it has an electron in a 2s orbital, and it has a filled 1s orbital. And so then the filled orbitals, they're closer to the nucleus, and they sort of screen the nuclear charge. And so that the 2s electron experiences a charge that's more akin to it's going to be less, the effective charge is going to be less than the full sort of charge of lithium. Lithium nucleus having a +3 charge. And similarly for sodium, would have core electrons in the 1s, 2s, and 2p orbitals. Then there would be a single electron in a 3s orbital. And again, that outer electron, which dominates its chemistry, is going to be screened by these core electrons that are closer to the nucleus. And so that 3s electron is going to experience an effective nuclear charge that's less than the full nuclear charge of sodium, which would be, let's see, 1s, 2s, which would have a nuclear charge of 11. 11 times the charge of an electron. So this makes sense intuitively, right? If we have our nucleus, and then we have these electrons that are in the core, they're tight, they're close into the nucleus. And then we have an electron that's out here, and essentially if we anthropomorphize this outer electron a little bit, when it looks at this bunch of particles here, it sees an effective charge that's reduced because the electron and the nucleus, the core electrons and the nucleus are close together, and so they're going to have potentials of opposite sign that partially cancel each other, and so you end up with this kind of effective potential that's less than what you would expect for the bare nucleus. Right, so there's this shielding or screening of the core nuclear charge. And this makes sense intuitively. It also, of course, is going to occur even if you have two electrons in the same orbital. In that even if they're in the same orbital, some fraction of the time, say one of the electron is, since there's an electron cloud, some fraction of the time, one of the electrons is going to just probabilistically going to be a little bit closer to the nucleus, and the other electron, so when it's close to the nucleus, it's going to experience maybe the full nuclear charge. Let's say if we just had the helium system, but then the other electron, again, it's going to experience this electron-electron repulsion, but it's going to look like, when you actually plot out the potentials and add them together, it's going to look like there's an effective potential that's less than a full +2 nuclear charge. And that's going to occur, some fraction of the time for each electron. Some fraction of the time, one electron is going to be further away from the nucleus. And the other one's going to be closer, and so it would experience a net Coulomb interaction that would correspond to a nucleus with a smaller charge. And sometimes it's going to be closer, and the other one's going to be further away. And so we expect that if we introduce some kind of parameter associated with this, that we're going to see an effective nuclear charge of between +1 and +2. So that's what we're going to do. We're going to introduce an effective nuclear charge parameter, and that's very easy for us to do because, if you recall, we have this parameter sort of baked into our 1s wave functions. Our 1s wave function is there's some normalization stuff out front. There's a 1 over pi to a half, and then z over a naught, where z is the nuclear charge, a naught is the Bohr radius, e to the minus z r over a naught. And so we already have this z parameter, and what we can do, or z constant, we can replace right? We want to, it's not that we're lazy, but we want to go in baby steps, right? So we can replace z with an effective nuclear charge z prime, and then that will help simplify things. We end up with the same wave function that we use for the hydrogen case, We've introduced a variational parameter without adding a lot of complexity to our system. And again, we expect z prime to be z prime to be between +1 and +2, corresponding to our physical picture of sometimes the electron is closer to the nucleus and sometimes it's further away relative to the other electron, and so the sort of partial screening that we take into account using this effective nuclear charge parameter we expect this nuclear charge parameter to be between 1 and 2. So, and one thing that's really nice about this wave function, it's normalized. Even when we vary z, if we replace z with z prime, we still end up with a normalized wave function because it has this normalization constant out front that has a z over a aught in it. Okay, so then we can assume that our trial wave function, our variational wave function, is going to be psi 1s 1. It's going to be a function of our variational parameter z prime, as well as the coordinates r1, theta 1, and phi 1. And it's going to be a product of two wave functions, one for electron 1 and one for electron 2. Then our variational energy is given by the real Hamiltonian the expectation value of the real Hamiltonian given the trial wave function. And we're going to actually call it E prime because we called Z, we replaced Z with Z prime, so we're going to call our variational switch and call that E prime. That's going to be our variational energy, and that's going to be, again, equal to this based on this expectation value expression. We're going to have an integral over all space of psi trial star, and then our real or true or complete Hamiltonian. So we have this sandwich between the trial wave function and its complex conjugate. We've sandwiched our Hamiltonian between those. And we could actually divide through by, in the typical typical variational approach, we would divide through by the integral of psi star trial psi trial in order to ensure normalization. However, we started with a wave function that is normalized regardless of the value of z prime, and so we don't need to do that. So that helps simplify things a little bit. And this is a big messy integral. That said, it can be solved exactly. And there are, I'm not going to go through the details of that. I don't want to get bogged down in that level of math unless it, unless it introduces some important concepts or intuition. In this case, it really doesn't. It's not pedagogically useful to run through that full integration, and it takes a lot of time. But we can give the result. So we integrate. The result is simple. We get E prime equals I'm going to use parentheses around our Z prime because otherwise it might look like Z to the 12th. So Z prime squared minus 27 Z prime over 8 times E squared over 4 pi epsilon naught A naught. So despite the fact that we end up with, we have a 6-coordinate integral, kinetic energy terms for both electrons and this electron-electron repulsion, and we have this variational parameter, we end up with, it integrates out, of course. When it integrates, that gets rid of all of the coordinates. So we integrated over the coordinates r1, theta 1, phi 1, r2, theta 2, phi 2, and we end up with an energy function that is only a function of the variational parameter, in this case Z prime. Okay, so, but this isn't quite an answer yet, right? What do we do next? Okay, then we have to go back to the variational method, which is take the derivative right, dE prime dZ prime, and we set it equal to 0. Then we solve for Z prime. And of course, if we take the derivative, and that gives us 2 Z prime minus 27/8 E squared over 4 pi epsilon naught A naught, and we set that equal to 0 and solve for Z prime. So first of all, we can divide both sides by E squared, where E is the charge of an electron, and we can multiply both sides by 4 pi epsilon naught A naught. So that simplifies things, and we end up with 0 equals 2Z prime minus 27/8, or, which, when we solve that, Z prime is 27/16. Okay, now is where we need to stop and think, does this make sense? Or did we make some conceptual error or some math error along the way that may be evident in getting some answer for Z prime that is outside the range of expected results. So it's good in these approximation methods to go in with some idea what you expect. So, and we did that. We decided, we introduced this effective nuclear charge parameter, and we said if there was no screening, if there was no effective nuclear charge issue, if there was no screening happening, that both electrons were feeling the full electrostatic interaction, experiencing the full electrostatic interaction with the nucleus, then we would expect Z prime equals 2. And on the other extreme, if the two electrons had 100% effective screening, in that one electron completely screens or to one full charge of the nucleus, then that would give, since the nuclear charge starts off at 2, that would bring us to a nuclear charge of 1. So we expected, as we stated above, that that Z prime would be in this range between 1 and 2. And in fact, it is, right? It's 27/16 is not exactly in the middle of the range, but 16/16 that would be Z prime of 1, and 32/16 that would be Z prime of 2. And so we're between, in the numerator there, 27 is between 16 and 32, and so it's in the range that we expected, which is a good sign, right? That's a quick consistency check to show that we're getting results that are consistent with expectations. So are we finished yet? No, we don't know yet what the energy is. So how do we find the energy? We plug our parameter back into our E prime, which is a function of Z prime expression, not the derivative, the original function that we started with, right? And then this gives us E prime. So we've essentially optimized our parameter. Then we take that parameter that we get, we plug it back into our energy expression. That'll give us our energy at the optimized value for that parameter. And when you plug all the numbers in, if we plug in E prime and we plug in Z prime is 27/16, and we put in E squared over 4 pi epsilon naught A naught, we get, in terms of electron volts, we get minus 77.5 electron volts. And the correct answer to 3 significant figs is minus 79.0 electron volts. And so this is about a 1.5 electron volt error. And again, this is an approximate result. We don't expect exact agreement. And our previous result was off by, I believe, 4.2 or something like that electron volts. So we've done substantially better. Okay, so now we have the energy. Now, and that's part of what we want to do. We also might want to know what's the size of a helium atom, right? What's the spatial extent of the wave functions? is what does 27/16 mean in terms of the size of the wave function? Well, we know that in our prior result, we had z prime essentially was for the case of z equals 2 or z prime equals 2. That was our initial guess before we introduced the variational parameter z prime. So, did I say 0? And again, as I said, what we ended up with as our variational result is 27/16, which is less than 2. And our wave function, if we kind of ignore the normalization constants, it's proportional to, so our variational or our trial wave function is proportional to e to the minus z prime r over a naught. So what happens, what's the difference between z prime equals 1 versus z prime equals 2 versus z prime, or sorry, z equals 1 versus z equals 2 versus z prime equals 27/16. And basically, the larger the value of z, the smaller the wave function, or z prime. And so essentially when we started off by ignoring, in the previous lecture, ignoring electron-electron repulsion, at least for calculating our wave function. And our wave function had z equals 2. When we introduced a variational parameter, let the wave function change its size, then when we added the z prime parameter and then let that get minimized, optimized to lower the total energy of the system, we get a larger wave function. Right? Smaller charge, smaller effective charge. Now we haven't actually changed the charge, right? It's a parameter. It's a parameter that represents electron-electron repulsion in an approximate way, essentially. And what happens is when we introduce that, we end up with a somewhat larger wave function, and that's because of we have two opposing forces. If z prime, if it were equal to 1, right, again, this is counterfactual, the wave function is too big, according to our energy calculations. It's too big. When it's that large, you get a non-optimal wave function size because if it's too big, the electron are too far from the nucleus. And so on average, the electron is not going to experience the full electrostatic attraction with the nucleus. It's going to be, on average, too far from the nucleus. If we have z prime equals 2, then our wave function is too small. Z prime equals 2 is great for optimizing the interaction between each electron and the nucleus. However, because the electrons are small and overlapping the same region of space, there's going to be too much electron repulsion. And therefore, z prime of 27/16 is just right. It balances these two sort of forces. That a smaller wave function optimizes your interaction with the nucleus, but a smaller wave function also gives you increased, because both electrons are going to have the same shape of the wave function. If they're going to be occupying the same region of space, there's going to be a lot more electron-electron repulsion. And so that z prime equals 2 would be a wave function that's too small, and there's too much electron-electron repulsion. The energy is not optimal. But if we have 27/16, that's right in between the two, and there's a balance such that the overall net energy of the system is reduced. And so, I can kind of think of this opposing forces and a kind of Goldilocks effect. The z prime equals 1 gives you, wave functions that are too big. Z prime equals 2 gives you a wave function that's too small. Z prime is 27/16 is just right. And a couple of final comments about this. We think of Z prime as being this effective nuclear charge parameter, but Z prime does not actually change the nuclear charge. And we can really think of it better as it's representing electron-electron interactions. It's sort of implicitly taking into account or including electron-electron repulsion. Even though we didn't necessarily initially formulate it in that way, right? We thought of it as each electron partially canceling the nuclear charge that the other electron experiences. However, the full electron, and this is important, the full electron-electron repulsion is included in the Hamiltonian, and in the theory as a whole, as right, even though it's not explicitly included in the wave functions, it is included in the Hamiltonian, and the electron-electron repulsion effect is manifest in the fact that we end up with an effective nuclear charge that slightly makes a slightly larger wave function than one would expect if you ignored electron-electron repulsion. So it's in there. It's just sort of implicit in the integrals. Okay, and so we've included electron-electron repulsion in this model in an approximate way, but it's in there. And we have sort of solved the helium atom problem. However, we've ignored electron spin. And it turns out that proper accounting for electron spin is really important, and we can't just, it's a little bit more complicated than what one might guess based on how the concept of electron spin is handled in Gen Chem and OChem classes. And so it turns out that there's a problem with electrons in that they're identical particles. And so we need to carefully construct our wave functions to properly take into account the fact that electrons are identical particles. And we'll talk about that and what's called exchange symmetry. Yeah, electron spin and exchange symmetry will be the subject of the next video.